Our next speaker, our last speaker of this session is Daniel Clark from Macalester College. He will be speaking on dynamics from the Maurer-Cartan forms and nonlinear realizations.
Yep, so like Ben said, I'm from Macalester College. I worked with Professor Thomas Terveldhuis over the summer on dynamics from nonlinear realizations. So this will be somewhat of a theoretical detour, but I hope to keep you all engaged. So before I get too far ahead of myself, I want to talk about a fundamental concept in physics, which is that of symmetry. So in physics, we say a system has symmetry if its action is left invariant under some kind of transformation. And there are discrete symmetries as well as continuous symmetries. And Noether's theorem shows why continuous symmetries of a system's action is so important to physics. Example of a discrete symmetry would be like the discrete rotational symmetry of a square. So the shape of the square is left invariant only under discrete angles, like 90 degrees, 180, 270, etc. If I were to rotate it by 45 degrees, clearly it's not left invariant. So that is an example of a discrete symmetry. We'll be focusing on continuous symmetry, which would be like the rotational symmetry of a sphere. Now, this shape is left invariant under continuous angle transformations. And so that would be an example of a continuous symmetry. And these kind of transformations belong to continuous groups, which we can call Lie groups. For our purpose, they're simply groups with continuous transformation parameters. Now, these groups also have corresponding Lie algebras, which we can think of as like the rules of the game, so to say. And in general, these algebras are constructed by introducing a particular product that satisfies the following conditions, those being bilinearity, alternativity, and finally the Jacobi identity. In our case, this product is the commutator. That is, the commutator of x and y is equal to x times y minus y times x. An example of a Lie group would be like the rotational symmetry that we just discussed for a sphere in 3 dimensions. This group is called SO3, or special orthogonal in 3 dimensions, and the generators for its Lie algebra are pictured here at the bottom left. Importantly, it's possible to obtain the group elements of this group by exponentiating these generators. And it might be a little weird to think, well, exponentiating matrices, what does that mean? Well, it's better to interpret these using Taylor expansions. So an example with like the x component of the angular momentum in 3 dimensions, if we exponentiate it with some transformation parameter theta, you can see at the top line here, I'm just writing out the Taylor series with the matrix multiplication not yet done. The next line, I've done the matrix multiplication. And those keen on this, or maybe like to do Taylor expansions in their free time, will note that the blue looks an awful lot like the sine theta expansion, and the green looks very close to the cosine theta expansion. It turns out that we can rewrite the previous slide in this way. And when we actually add those matrices together, we see we get the matrix at the bottom, which is the rotation about the x-axis. So that's a very provocative result. Also, we can very concisely write these Lie algebras using commutation relations, or the commutator. So there are a couple things here that might not be super familiar, those being the Einstein summation convention and the Levi-Civita tensor. These are like the tools of the trade for a lot of field theories and other applications to physics. So the Einstein summation convention states that when we see repeated indices, we sum over them. And the Levi-Civita tensor is generally, you set a certain permutation of the indices to be +1, and then even permutations of that will keep the sign, while odd permutations will flip the sign to a minus. So like, for example, an odd permutation would be like if I swapped 1 and 2. So epsilon 1, 2, 3 is +1, epsilon 2, 1, 3 is -1. Also, this tensor is anti-symmetric, so if any of the indices are equal, that's 0. So epsilon 1, 1, 3 would be 0. An example of combining these together would be like if I take the commutation relation between the x and y component of the angular momentum, some object. I write it down here in full. and we see that the first two terms, or I guess I should say that we have epsilon 1 to k, and then L sub k. So that index is repeated, meaning we need to sum over it. So we have epsilon 1 to 1, L1, and so on and so forth. But those first two terms, again, because the Levi-Civita tensor is antisymmetric, vanish, and we're left with only the last one, which is what we expect. Furthermore, covariance and invariance are very important to physics, especially when constructing an invariant action. And an example of a covariant object in SO3 is a vector. We call it covariant because they transform with the generators, in this case being matrix multiplication. And a quantity that is invariant can be constructed out of these covariant objects. This quantity is the dot product. For example, if I define some vector x, y, z, I can see that its dot product is x squared plus y squared plus z squared. Now, if I transform this vector under a rotation, maybe about the x-axis like earlier, and I take that dot product with itself, I find I get the exact same quantity. Again, just reiterating, it is invariant out of these covariant building blocks. Great. So far, we've talked a little bit about symmetries, group algebras, obtaining group elements, some tools of the trade, and these covariant building blocks, which will lead to invariant quantities. Okay. So to move on, I want to extend this 3D rotation group to both include a temporal dimension, as well as space-time translations and Lorentz transformations. So because I can write these algebras very concisely with commutation relations, this group that I just mentioned with the space-time translations, etc., is called the Poincare algebra. And its commutation relations are pictured here. The P is the form momenta of the object, while the N corresponds to the Lorentz generator. That eta there is also the Minkowski metric corresponding to a flat spacetime. And with this algebra specified, we can start to get ideas about dynamical information. We begin this method of nonlinear realizations with the Coset construction. And so one way to do this is to divide out the rotations from the Poincare group, which would leave only like the space-time translations. So before, remember, we could exponentiate these generators in order to obtain group elements. So here, we're exponentiating the generator responsible for space-time translations. Now we get to the Maurer-Cartan form, which are like the building blocks. There's a rigorous mathematical definition for this, but for our purposes, we can really just consider it as an object carrying the basic information about the structure of the group we're considering. And it's defined in this way, as the inverse of the coset with its exterior derivative. As for actually calculating the Maurer-Cartan form, we need to make an addition to our tools of the trade, which are the Baker-Campbell-Hausdorff formula. These are a little bit complicated, and there are several of them, but in this case, we only need this one. And we find that middle equation with the omega minus 1 is our Maurer-Cartan form. And furthermore, we want to define this new quantity, this small omega, and that will be our covariant building block when we try to construct an invariant action from which we will then get our dynamics. So, like I said, with this building block, we can start thinking about this action and Lagrangian and Euler-Lagrange equations and all that good stuff. But in fact, it's actually helpful to define another quantity, which is kind of inspired from field theory, but for our purposes, we can just define it in this way. And interestingly, when we contract that with the eta metric, it's invariant. And this is analogous to like a dot product, where we're taking the components of each vector and multiplying and adding them together. That's very similar. Here, I'm using the Einstein summation convention again. We're summing over these indices. And in fact, the Lagrangian from these covariant building blocks will take this form that I have pictured at the bottom. And incredibly, this is the action corresponding to a relativistic massive free particle. So those are some already very cool dynamics from this kind of nuanced method. Now, that's very good. What if we want something more interesting? Maybe we can change the rules of the game a little bit. Instead of just having the Poincare algebra, we can extend it to something called the Maxwell algebra. So we do this namely by making the form momenta no longer commutative. So if you notice, these are the main differences between the Poincare algebra and the Maxwell algebra. In yellow, like I said, the four momenta is no longer commutative, and now their commutator gives us this tensorial charge, is something we can think of. Now, because we have this new object, we need to further define its commutation relations with the rest of the algebra, that being the Lorentz generator, the four momenta, and itself. So with this definition, we can update our coset element, include exponentiation of that generator, the zmn, with the parameter theta mn. And we do require more Baker-Campbell-Hausdorff formula to actually get the Maurer-Cartan form. But once we do that, we can again write this MC form in terms of these covariant building blocks, the omega p and the omega z. And then with those covariant building blocks, we are able to construct our Lagrangian, our invariant Lagrangian. And if we define this tensor FAB in this way, we can get these really compact, nice-looking equations of motion. These are our, after solving the Euler-Lagrange equations associated with this Lagrangian, we get the equations at the bottom here. Of course, now that we have these equations, it's time to physically interpret them, right? So as a reminder, the covariant relativistic Lorentz force looks like this. It's the proper time derivative of the four momenta. We're saying that that's equal to the charge times what's known as the electromagnetic field strength tensor, which contains information about the electric field and the magnetic field. And then that multiplied by the proper time derivative of the x coordinate. Note that the dot is specifically with respect to proper time, not coordinate time, which is manifestly relativistic. And this looks a lot like what we have on the bottom right, because the four momenta, as a reminder, again, is like mass times acceleration, right? And acceleration is like the second time derivative of x. So these look very, very similar. And in fact, if we define our lowercase FAB in an appropriate manner, they're actually the same equation. And so that's incredible. And really what it means is that we've retrieved the dynamics for a relativistic, charged, massive free particle in an electromagnetic field. Note that the bottom left equation there states that this tensor, this field strength tensor, is constant, right? Because it's not changing in time. So this electromagnetic field is constant. It is not changing in time. And so just to sort of reiterate as a conclusion, we can apply the method of nonlinear realizations, which is this coset construction with a Maurer-Cartan calculation. We can apply that method to particle mechanics, obtain an invariant action that's invariant under some group, and then apply the Euler-Lagrange equations, solve them, and get incredible dynamics. But notably, the upshot of my project that I worked on over the summer is that if we use this method to make an action that is invariant under the Maxwell group, we get the dynamics, again, of a massive relativistic charged particle and a constant electromagnetic field. And that's my talk. I guess I can open it up for questions now.
Great talk, Daniel. Are there any questions?
Non-technical question, quick. So is this like independent research you're doing as part of physics, or are you doing this on the side without any credits, or is this being added to, say, like a class that you're doing where you're getting independent credit for it?
This was an expansion of tools I learned over the summer working with Professor Thomas Terveldhuis. He had done a paper on brain dynamics using this method, and I was applying it, which is a more like field theory approach, whereas I'm applying it to particle theory. And there's extensions of this work that can be used to include things like spin for spinning charged particles, and also considerations for gravity. there's a lot of future work that could be done with this that I'm keen on pursuing.
Okay, no, you just answered my question with your first sentence there. So you started working on this over the summer as a, okay, all right. So it was not part of a class project that just kind of grew out and it was separate research. Okay, cool. Thanks.
Great. So Demos, I think the next event is actually going to be at 11. Is that correct? Okay, so folks, let's thank all of our speakers. Fantastic job today. I definitely know I learned some things, both about physics and about Zoom, so that was great. I am placing in the chat a Google form so you can offer a nomination for the talk that you thought best. And then I believe, Demos, this is the main room, correct?
This is the main room.
And so the next event at 11 on NASA Center internships will be in this room. Right. If anybody's having any problem getting into that form, I believe it does request that you use your Google account, but otherwise it should work. So, okay. Thank you again to everyone for your talks today. That was fantastic.
Thank you, Ben and Demos.
You're welcome.
Thanks to all. Great.